Go outside on a clear day and feel the sunlight on your skin. That warmth has crossed 93 million miles of empty space to reach you, and it was born in a place no human will ever visit, the core of the sun. Every second, the sun crushes 600 million tons of hydrogen so hard that it becomes something new, and a sliver of that matter simply vanishes and turns into light. We call it fusion. It is the engine of every star, and it forged the iron in your blood and the calcium in your bones. For 100 years, we have dreamed of lighting that same fire here on Earth, inside a machine, on purpose. And in a quiet field in the south of France, 35 nations are now trying to do exactly that, building the largest scientific machine in human history to hold a piece of a star. They named it ITER, which in Latin means the way. This is the story of how the stars burn and how we are finally learning to build one of our own. To understand the machine rising in France, we have to begin somewhere unexpected. Not in a laboratory and not among the stars, but inside the smallest thing there is. We have to begin inside the atom. Everything you have ever touched is built from atoms, and they are almost unimaginably small. There are more atoms in a single glass of water than there are glasses of water in all the oceans of the Earth. For thousands of years, nobody even knew they existed. The ancient Greeks merely guessed there might be some smallest, uncuttable piece of matter and gave it the name atomos, meaning uncuttable. And for the alchemists of the Middle Ages, the dream was to discover the secret rules of matter and use them to turn cheap lead into precious gold. They failed, of course, because they were chasing magic. But hidden inside their failed dream was a real and astonishing truth that science would not uncover for centuries. There really is a way to turn one element into another. The stars do it every second, and it releases more energy than the alchemists could ever have imagined. For a long time, scientists pictured the atom as a solid little ball. Then, in 1909, a physicist named Ernest Rutherford ran one of the most important experiments ever performed. He fired tiny, positively charged particles at a sheet of gold foil so thin it was nearly transparent, expecting them to sail straight through. Almost all of them did. But every so often, one would ricochet violently backward as if it had struck something incredibly hard and small. Rutherford said it was as astonishing as firing a cannon shell at a piece of tissue paper and having it bounce back and hit you. From that bounce, he realized the truth. An atom is almost entirely empty space, but at its very center sits a minuscule, dense, positively charged core. He called it the nucleus. So picture an atom now as a tiny solar system. At the center is that dense nucleus, and whirling around it in a blur are even tinier particles called electrons. The nucleus itself is built from two kinds of particles. There are protons, which carry a positive electric charge, and neutrons, which carry no charge at all. And here is the single most important fact in all of chemistry. What makes one element different from another is nothing more than the number of protons in its nucleus. One proton, and you have hydrogen, the lightest and most common substance in the universe. 2 protons, helium. 6 gives you carbon, the backbone of all life. 8, oxygen. 26, iron. 79, gold. Change the number of protons, and you have changed the very identity of the matter itself. The neutrons matter too in a subtler way. An element always has the same number of protons, but it can come in versions with different numbers of neutrons. We call these versions isotopes. Ordinary hydrogen is just a single lone proton with no neutron at all. But add 1 neutron, and you get a heavier hydrogen called deuterium. Add 2 neutrons, and you get a heavier still and slightly unstable hydrogen called tritium. Remember those 2 names, deuterium and tritium, the heavy hydrogens. They are the exact fuel that ITER will burn. And they are the same fuel that, in their own way, the stars know well. Now we arrive at a beautiful problem. You may remember that with magnets, opposite poles attract and like poles repel. Push two north poles together and you can feel them fight back. Protons all carry the same positive charge, so inside a nucleus, every proton is frantically trying to shove every other proton away. A nucleus crammed with positive charges should, by all rights, instantly tear itself to pieces. To see why it doesn't, you have to know that the universe runs on just 4 fundamental forces, and everything that ever happens, anywhere, is one of them at work. The first is gravity, the gentle, endless pull that holds you to the Earth and the Earth to the Sun. Gravity is actually by far the weakest of the 4, but it reaches across infinite distance and only ever pulls, never pushes, so across the vastness of space, it adds up and rules the cosmos. The second is the electromagnetic force, the push and pull of electric charge and magnetism. It is far stronger than gravity, and it is what makes the protons repel. But there are 2 more forces, and they only operate deep inside the nucleus, across distances almost too small to imagine. One is called the weak nuclear force, and we will meet it inside the Sun, where it does something quietly miraculous. And the other is the strong nuclear force, and it is, up close, the strongest force in all of nature. The strong force is the glue of the nucleus. Right up close, it utterly overpowers the electric repulsion and clamps the protons and neutrons into a tight little knot. But it comes with a strange and crucial catch. It only reaches across distances smaller than the nucleus itself. The particles have to be practically touching for it to take hold. Bring 2 protons close enough, within a hair's breadth of contact, and the strong force seizes them and snaps them together with tremendous power. Keep them even slightly apart, and the electric repulsion wins, and they hurl each other away. The entire story of nuclear energy and of the stars and of ITER lives in that razor-thin gap. To get the energy out, you have to force the protons across the moat of their own repulsion, close enough for the glue to grab. Because when the strong force does win, when particles lock together, something almost magical happens. The bundle they form weighs a tiny bit less than the separate pieces did on their own. That missing mass did not disappear into nothing. It was released as a flash of pure energy at the very moment the pieces joined. The more tightly they bind, the more energy escapes. Scientists call this the binding energy, and when they carefully measured it for every element and drew it on a graph, they uncovered one of the most important shapes in all of science. The line climbs steeply from the lightest elements, rises to a single highest peak, and then slopes gently back down toward the heaviest. And sitting alone at the summit, the most tightly bound and most stable nucleus in all of creation, is iron. Iron is the mountaintop of the atomic world. And that one fact, that iron sits at the very top, is the master key that unlocks both ways human beings have ever released the colossal energy locked inside the atom. Because there are exactly 2 ways to roll downhill toward iron, and rolling downhill always sets energy free. The first way is to begin with something very heavy, sitting far down the slope on the other side of the peak, and break it into smaller pieces that are closer to iron. We call this fission, which simply means splitting. Take a heavy, restless atom like uranium, fire a single neutron into it, and the whole nucleus shudders and cracks apart into 2 lighter atoms, plus 2 or 3 spare neutrons, plus a burst of energy. And here is the clever and dangerous part. Those spare neutrons go flying off and split more uranium atoms, which release still more neutrons, which split still more, a cascade we call a chain reaction. Pack enough uranium together, more than a certain amount called the critical mass, and the chain becomes self-sustaining. Tame it carefully inside a reactor, and the heat it makes will boil water, spin a turbine, and light a city. Let it run wild, and you have a bomb. This is nuclear fission, and right now it powers every nuclear plant on Earth. The second way to reach iron is to come at the peak from the opposite side, to start with the very lightest atoms, like our heavy hydrogens, and join them into something a little heavier and more tightly bound. This is fusion, which means joining. And because that binding slope is so wonderfully steep down at the light end, fusion releases even more energy, pound for pound, than fission does. In fact, the specific reaction ITER will use, fusing 1 deuterium and 1 tritium, produces a single helium nucleus and 1 fast-flying neutron, and it releases several times more energy per pound of fuel than splitting uranium ever could. Most of that energy is carried away by the neutron, and capturing it is exactly how a future fusion plant would make its heat. So here is the obvious question. If fission already works, and we already use it everywhere, why go to all the impossible trouble of fusion? Because fusion, if we can ever truly master it, is better in nearly every way that matters. The fuel is limitless, because deuterium can be sieved straight out of ordinary seawater, enough to power our civilization for millions of years. The waste is far kinder, because fusion makes no fragments that stay deadly for tens of thousands of years, only harmless helium and a machine that grows mildly radioactive and then cools off in about a century. And the safety is built into the physics itself. A fusion reactor cannot melt down because there is no chain reaction to run away, and at any instant it holds only a puff of fuel lighter than a postage stamp. If anything goes wrong, the delicate fire simply goes out on its own. It cannot explode. It can only fail safe. On paper, fusion is the most beautiful source of energy our species has ever conceived. There is just one catch, and it is an enormous one. To understand it, we have to travel to the only place fusion has ever truly worked. We have to go inside a star. The sun has been fusing hydrogen for 4.5 billion years, and it makes the whole business look effortless. But for a long time, the sun hid a secret that nearly broke the science of the 19th century. The puzzle was simple to state. What makes the sun shine? Every energy source anyone could imagine came up hopelessly short. If the sun were a giant ball of burning coal, it would have turned to cold ash in a few thousand years. One of the greatest physicists of the age, Lord Kelvin, calculated that even if the sun were slowly shrinking under its own gravity and releasing heat as it collapsed, it could shine for only about 20 or 30 million years. That sounded like plenty, until the geologists and the biologists arrived with an awkward fact. The rocks of the Earth, and the slow story of evolution written into them, proved beyond any doubt that the sun had been burning steadily for billions of years, not millions. The numbers were off by a factor of 100. Something utterly unknown was keeping the sun alight. The answer came in 1920 from a British astronomer named Arthur Eddington. Drawing on Einstein's brand new and still shocking idea that mass and energy were two faces of the same coin, Eddington made a bold guess. Deep in the sun's core, he proposed, hydrogen was being fused into helium, and the tiny scrap of mass lost in the process was pouring out as sunlight. Almost no one believed him at first. He had no proof, only a hunch and an equation, and other physicists objected that the sun simply wasn't hot enough to do it. Eddington's famous reply was that the skeptics should go and find a hotter place. He stood his ground, and he wrote with breathtaking foresight that one day this same power might be harnessed for the well-being of the human race or its suicide. 2 decades later, in the late 1930s, a physicist named Hans Bethe worked out the exact chain of nuclear reactions that powers the sun, step by careful step. It was such a monumental achievement that it would one day win him the Nobel Prize. The ancient question, what lights the stars, finally had its answer. And the answer was fusion. So how does the sun actually do it, when we just spent a whole chapter learning how stubbornly protons refuse to touch? The sun's first secret is not heat, it is sheer, crushing size. You could line up more than 100 Earths across the face of the sun, and pour more than 1 million Earths inside it, and every ounce of that titanic mass pulls inward under its own gravity. There is a beautiful balance at work here that keeps the sun stable, called hydrostatic equilibrium. Gravity is forever trying to collapse the sun inward, and the outward pressure of the hot gas is forever trying to blow it apart, and the two are locked in a perfect, self-correcting standoff. If fusion ever sped up, the core would heat, push out, and cool itself back down. If it slowed, the core would shrink, heat up, and speed itself back up. A star is a furnace that automatically holds its own thermostat for billions of years. The squeeze at the sun's center is almost beyond comprehension, hundreds of billions of times the air pressure around you, and it heats the core to about 15 million degrees. At that temperature, hydrogen stops being a gas. It is not solid, liquid, or gas at all. It has become a fourth state of matter, called plasma. Here on the cool surface of the Earth, we live among only 3 states. Ice is solid, water is liquid, steam is gas. But heat a gas fiercely enough, and its atoms collide so violently that the electrons are stripped clean off, leaving a churning soup of bare, positively charged nuclei and free-flying negative electrons. That is plasma. It feels exotic to us, but it is in fact the most common state of ordinary matter in the entire universe. Every star is a sphere of it. The neon in a glowing sign, a bolt of lightning, the tail of a comet, all are plasma. More than 99% of all the visible matter in the cosmos is plasma. The universe is, overwhelmingly, made of fire. Now we come to the actual machinery of the sun, and it is more wonderful and more delicate than you might guess. To turn 4 hydrogen nuclei into 1 helium nucleus, the sun runs a series of steps called the proton chain. And the very first step is the hardest, slowest, and most surprising of all. 2 protons must come together and stick, but a pair of protons alone cannot form a stable nucleus. For them to bind, one of the 2 protons has to transform in that very instant into a neutron. And the only thing in the universe that can perform that transformation is the 4th and faintest of our forces, the weak nuclear force. It is so feeble, and the chance of it acting at just the right moment is so vanishingly small, that an average proton in the sun's core will wait billions of years before it successfully fuses. That is the real reason the sun burns slowly and steadily instead of exploding. The weak force throttles it. If that first step were easy, the sun would have detonated long ago. Its gentleness is the reason you are alive. But even getting 2 protons close enough to give the weak force its rare chance runs into the problem we already know. At 15 million degrees, the protons still are not moving fast enough to truly touch. And here the universe pulls off one of its strangest tricks, a ghostly rule of the world of the very small called quantum tunneling. In our everyday world, if you do not have enough energy to roll a ball over a hill, the ball just rolls back. But in the quantum world, a particle facing a barrier it cannot possibly climb can, very occasionally, simply appear on the far side, as though it passed straight through the wall. A physicist named George Gamow worked out the mathematics of this in the 1920s. Tunneling almost never happens, and the odds against any 2 particular protons are astronomical. But the sun's core is so unthinkably vast, and packed with so many countless protons colliding over and over, that even the rarest stroke of tunneling luck happens often enough, somewhere every instant, for fusion to proceed. The sun runs on a force too weak, and a trick too rare to power anything, multiplied by a number too large to picture. And once the chain gets going, the dominoes fall. Through its patient steps, 4 hydrogen nuclei are welded into a single nucleus of helium, plus a couple of ghostly particles called neutrinos that stream out untouched. And the helium that results weighs about 0.7% less than the 4 pieces that made it. That vanished sliver of mass becomes energy, following the most famous equation ever written, Einstein's discovery that energy equals mass times the speed of light, multiplied by the speed of light again. Because you multiply by that enormous number twice, even a microscopic loss of mass blossoms into a tremendous flood of energy. That flood is sunlight, but its journey out is almost as wondrous as its birth. The energy is born in the core as a flash of light, and then it begins one of the slowest journeys imaginable. It is absorbed and spat out, again and again, by the dense plasma above it, staggering outward in a drunken zigzag we call a random walk, taking, on average, tens of thousands of years just to crawl from the core to the surface. Then, free at last, it leaps across space to the Earth in only 8 minutes. So the sunlight warming your hand right now left the sun's surface about 8 minutes ago, but the energy inside it was born in the core back when our distant ancestors were first learning to tame fire. And the sun is only the opening chapter of a grander story. As larger stars age and burn through their hydrogen, their cores grow hotter still, and they begin to fuse helium into carbon, carbon into oxygen, building heavier and heavier elements like rungs on a ladder, always climbing toward that summit, iron, and always stopping there because to fuse past iron would cost energy instead of releasing it. To forge the elements heavier than iron, the gold in a wedding ring, the silver in a spoon, the universe needs something more violent than any ordinary star. It needs the cataclysm of a dying giant exploding as a supernova, or the unimaginable collision of the dense stellar corpses such explosions leave behind. In those few seconds of cosmic fury, the heaviest atoms are hammered into being and flung across the galaxy, to drift for ages and one day gather into new stars, new worlds, and new living things. So when scientists tell you that you are made of stardust, understand that this is not a poem. It is a laboratory fact. Every atom in your body heavier than hydrogen was cooked inside a star that lived and died before the sun was born. We are the ash of ancient fire, briefly woken up, gazing back at the sky and asking how the fire works. And now, having learned the answer, we have set ourselves the most audacious task in our history. We have decided to build a star of our own. If the sun fuses hydrogen with gravity, the obvious question is, why can't we simply copy that on Earth? The answer is humbling. Gravity only becomes a furnace mighty enough to drive fusion when you have an entire star's worth of mass to do the squeezing. We do not have that. We have a building. And a building has the gravity of a building, which is to say, almost none. So if we cannot crush our hydrogen the way the sun does, we are forced to make up the difference somewhere else. To see where, you need the three things that every fusion attempt, in a star or in a machine, must achieve all at once. Scientists fold them into a single rule, but you can think of it as a recipe with three ingredients. You need the fuel hot enough, dense enough, and held together long enough. Hot enough, so the nuclei move fast enough to tunnel together and beat their repulsion. Dense enough, so they are packed and collide often. And held together long enough, so that enough of those collisions occur before the precious hot fuel flies apart and cools. Temperature, density, and time. Multiply those three numbers together and you get what physicists call the triple product. And only when that triple product climbs high enough does a fire light that produces more energy than it took to start. For 70 years, the entire global effort in fusion has been a quest to push that one number higher. The sun wins the recipe through brute density and endless patience. Its core, as fusion goes, is not even very hot, only 15 million degrees, but it is crushed denser than solid lead and held there by gravity for billions of years. It trades a modest temperature for staggering density and time. On Earth, we cannot come anywhere near that density, and we certainly cannot wait billions of years. So we are forced to crank the one knob we can reach, temperature. To fuse hydrogen in a machine, where the fuel is millions of times thinner than the heart of the sun, we have to heat it to around 150 million degrees, roughly 10 times hotter than the very center of the sun. To copy the gentlest furnace in the sky, we have to manufacture the single hottest place in the entire solar system, on the ground, in a room, on an ordinary afternoon. And that lands us on the riddle that has tormented physicists for 70 years. What could you possibly build a container out of to hold something 150 million degrees hot? Steel melts at around 1500 degrees. Even diamond would flash instantly into vapor. Any wall you build will be destroyed the moment the plasma touches it, and worse, that touch would chill the plasma and snuff out the fusion. You need to hold a star in your hands without anything actually touching it. There are exactly 3 known ways, and we can cross the first, gravity, off our list at once, because it only works if you happen to have a few 100,000 Earths to pile up. That leaves 2 methods human beings can actually attempt. The second method is the clever one, and it rests on the single beautiful fact that a plasma is electrically charged. Drop a charged particle into a magnetic field, and a rule called the Lorentz force takes hold. The particle is not free to fly wherever it likes. Instead, it is forced to spiral, winding tightly around the invisible magnetic field lines like a bead threaded on a wire, gliding freely along the line but unable to cross sideways off of it. This is the deep secret of the whole approach. If you cannot hold the plasma with a wall of matter, you can hold it with a wall of pure magnetism, a cage with no sides you could ever see or touch, because the charged particles are chained to the field lines and simply cannot wander away. This is magnetic confinement, and it is the path ITER follows. But there is a wrinkle. Build a simple straight tube of magnetic field, and the plasma spirals merrily along it, and then shoots straight out both open ends, like water from a hose. The fix, dreamed up in the 1950s, is gorgeous. Bend the tube around into a circle, a donut, so that it has no ends at all. Now the particles can spiral around and around the ring forever, never finding an exit. It turns out a single looping field is still not quite enough, because subtle drifts nudge the particles toward the walls, so a tokamak adds a second trick. It drives a powerful electric current through the plasma itself, and that current wraps an additional magnetic field the short way around the donut, so the total field gently corkscrews around the ring in a helix. That twist is the secret that keeps the plasma stable and centered. A close cousin, called the stellarator, achieves the very same twist without any current in the plasma at all, by instead bending its external magnets into fantastically complex, sculpted shapes. Both are magnetic bottles holding the untouchable with the invisible. But a magnetic bottle only holds the fuel. You still have to heat it to 150 million degrees, and that takes 3 ingenious tricks layered together. The first is the plasma's own electric current, which meets resistance and warms the gas, the same way an old toaster wire glows, though this only carries you part of the way. The second is to fire beams of fast neutral atoms deep into the plasma, where they collide and dump their energy like a cue ball scattering a rack. And the third is to bathe the plasma in powerful radio waves and microwaves tuned to the exact frequency at which the particles already spiral, so the energy is absorbed in perfect resonance, the way a pushed swing climbs higher when you push it in rhythm. Layer these together, pour in enough power, and the gas climbs past every temperature in the solar system. With the fuel finally hot enough, the real prize comes into view, and it arrives in 2 levels. The first is called break-even, the moment a plasma at last gives back as much energy as you poured in to heat it, the point where that triple product of temperature, density, and time climbs just high enough to balance the books. But the true dream lies one step beyond, and it has a name of its own: ignition. Remember that when deuterium and tritium fuse, they make not only an escaping neutron, but also a charged helium nucleus, and that helium, being charged, stays trapped in the magnetic cage. As it ricochets around, it dumps its energy back into the plasma, heating it from within. Let enough helium build up, and the plasma begins to keep itself hot, the fusion sustaining its own fire with no outside help at all, exactly the way the sun does. That is ignition, a true self-sustaining star in a bottle, and it is the summit every fusion scientist is climbing toward. Engineers have even tried reshaping the bottle to reach it faster. Squeeze the donut inward until its central hole nearly closes, and it becomes a cored apple in earnest, a design called the spherical tokamak, rounder and tighter and, some of the newest private companies are betting, a faster and cheaper path to that self-sustaining flame. The third and final road to fusion takes the complete opposite approach. Instead of holding a thin plasma gently for a long time, what if you held it for almost no time at all, but squeezed it unbelievably hard for that single instant? This is inertial confinement. You take a tiny pellet of frozen hydrogen, no larger than a peppercorn, and you blast it from every side at once with the most powerful lasers ever built. The surface erupts, and like a rocket firing inward, it implodes the fuel to a density greater than the center of the sun for just a few billionths of a second. In that vanishing flicker, before the fuel can blow itself apart, the triple product spikes and it fuses. The plasma's own inertia, its sheer reluctance to move, is the only thing confining it, which is where the name comes from. America's National Ignition Facility, where 192 giant lasers converge on a target the size of a peppercorn, is the great temple of this approach. Magnetic confinement holds a thin plasma gently for a long time. Inertial confinement crushes a tiny plasma violently for an instant. 2 completely different strategies, climbing toward the very same summit. They sound almost simple, laid out in clean sentences. But behind them lie 70 years of failure and genius, and a cast of characters as strange and brilliant as any in the history of science. The dream of building a star did not begin with engineers. It began, as we have seen, with Eddington's daring guess. But knowing what powers the stars and being able to do it yourself are 2 very different things. And the first time humanity reproduced the fire of the stars on Earth, it was not to power a city. It was to build the most terrible weapon ever made. The deeper science came first. Through the 1930s, Hans Bethe and others mapped not 1 but 2 ways stars fuse hydrogen. In smaller stars like the Sun, it is the proton-proton chain we have met. But in larger, hotter stars, fusion runs through a clever cycle in which carbon, nitrogen, and oxygen act as recyclable helpers, passing protons along an assembly line and emerging unchanged at the end, ready to go again. That cycle is called the CNO cycle, and understanding it told us how nearly every star in the sky earns its light. The stars had given up their oldest secret. The question now was whether human hands could ever repeat it. In the early 1950s, in the long shadow of the Second World War, scientists in the United States raced to harness fusion for a bomb. The physicists Stanislaw Ulam and Edward Teller found the key, and on the first day of November 1952, on a tiny atoll in the Pacific Ocean, the United States detonated the first true hydrogen bomb. Its code name was Ivy Mike. For a fraction of a second, it became an artificial star, fusing hydrogen in a flash far brighter than the sun, and when the light faded, the island it had stood upon was simply gone, vaporized, replaced by a crater in the sea. The hydrogen bomb proved beyond any doubt that fusion could be ignited on Earth. But a bomb is fusion unleashed all at once, for less than a heartbeat, a single catastrophic scream of energy. The far greater prize and the far harder one was controlled fusion. Not a flash, but a steady, governable flame you could feed and tend and switch on each morning to light a town. And so, even as the bombs were built, a second and very different quest began, quietly, in laboratories on both sides of a world dividing into Cold War. In the United States, an astrophysicist named Lyman Spitzer was riding a ski lift in Aspen in 1951 when, turning the problem of trapping a plasma over in his mind, he conceived an elegant, twisted machine he would name the Stellarator, after the stars themselves. He hurried back to Princeton and began to build it. And in the Soviet Union, two physicists, Igor Tamm and the brilliant, conscience-stricken Andrei Sakharov, who would later become as famous for his fight for human rights as for his physics, sketched out the very first tokamak. For years, on both sides of the Iron Curtain, progress was agonizing. Plasma turned out to be wild and treacherous, like trying to carry water in a net. It wriggled and bulged and writhed, found the tiniest flaw in every magnetic cage, and slithered out through it. Whole categories of instability were discovered, named and feared: the kink, the sausage, the tearing mode, each one a new way for the plasma to wreck itself. Machine after machine fell short. The fuel kept leaking away and cooling before it could ever fuse. Some began to whisper that controlled fusion might simply be impossible. For a stretch in the late 1950s and early 1960s, the whole endeavor nearly died of despair. The plasma kept bleeding its heat out through the magnetic field far faster than any theory predicted. A stubborn leak that came to be named Bohm diffusion, and some of the finest minds in physics quietly concluded that magnetic confinement might never work at all. Fusion research had begun as a tightly guarded military secret on both sides, each nation convinced it was on the verge of a breakthrough the other must not get first. But by 1958, with everyone equally stuck, the great powers did something almost unheard of at the height of the Cold War. They declassified their fusion research and laid it open to the world at a vast conference in Geneva, precisely because no one could crack the problem alone. The laboratories began, grudgingly at first and then eagerly, to compare their failures and share their hard-won tricks. That openness, born of shared frustration, would soon save the entire field. And then, in 1968, came the thunderclap. Soviet scientists announced that their latest tokamak, called T3, had reached temperatures and confinement far beyond anything any other design on Earth had managed, around 10 million degrees. The claim was so spectacular that Western physicists frankly refused to believe it. So the Soviets did something remarkable. At the height of the Cold War, with their two nations aiming nuclear weapons at one another, they invited a team of British scientists to come to Moscow, haul in their own delicate laser instruments, and measure the Soviet plasma for themselves. The British team came. They measured. And they confirmed that the astonishing Soviet results were absolutely real. It was an extraordinary moment, scientists reaching across the most dangerous divide on the planet to help a rival verify a breakthrough. And it changed the world of fusion overnight. Laboratories everywhere abandoned their old designs, including Spitzer's Stellarators, and rebuilt themselves as tokamaks. The Soviet donut had won, and the global race was truly on. Through the 1970s and 1980s, the tokamaks grew ever larger and more powerful. In America rose the tokamak fusion test reactor at Princeton, which in the 1990s would briefly produce 10 million watts of fusion power. In Europe, a consortium of nations built the Great Joint European Torus, JET, which switched on in 1983 in the English countryside and would hold the world's fusion records for decades. Each machine answered questions the last one could not, and each crept a little closer to the prize, that magic point where a plasma finally gives back more than it takes. But the scientists could all see the same mountain rising ahead, and it filled them with both hope and dread. The truly decisive machine, the one large enough to cross that line for good, would be so colossal and so expensive that perhaps no single nation on Earth could ever afford to build it alone. The dream might die not for lack of science, but for lack of partners. And then history opened a door no physicist could have planned. In November of 1985, in Geneva, the leaders of the two great superpowers, the United States and the Soviet Union, sat down together face to face for the first time in years. These were nations that had spent 4 decades aiming thousands of fusion bombs at one another, that had carried the world to the very brink of annihilation. And in the middle of all that fear and suspicion, amid bitter arguments over missiles and mistrust, they found one thing, just one, that they could agree to do together. Not to build a weapon, to build a fusion reactor. A machine to give the entire world clean and limitless energy. The bitterest enemies in human history, joining hands over the very fire they had each built to destroy the other, and choosing, for once, to aim it at the future instead. That handshake in Geneva was the seed, and from it would grow the most ambitious scientific collaboration our species has ever attempted, a machine called the Way. That seed took 20 years to flower. Designing the machine, deciding which nation would build which colossal piece of it, and choosing where on Earth to put it took years of patient and often difficult diplomacy. The choice of where to build it alone nearly fractured the whole partnership. 2 nations, France and Japan, each wanted the great machine on their own soil, and for months the negotiations deadlocked, the partners split between the 2 candidates. In the end, in 2005, they struck a bargain worthy of the project's whole spirit. The reactor would rise in France, while Japan would host other major research facilities, supply a large share of the leadership and key components, and share in the work. The rivalry that might have ended the dream was folded, instead, into the partnership. And in 2006, the agreement was finally signed, and it was unlike anything in the history of science. 35 nations joined as full and equal partners. All the countries of the European Union, together with the United States, China, India, Japan, South Korea, and Russia, together they represent more than half of every human being alive. They chose a site in the south of France, near a village called Cadarac, and they named their machine ITER, the Way. So what are they building? At its heart, ITER is a tokamak, that same Soviet donut, but built on a scale that staggers the mind. The hollow chamber where the plasma will live holds a volume of around 840 cubic meters, roughly 10 times larger than any tokamak ever built, big enough to swallow a small house, and shaped like a cored apple, a capital letter D spun all the way around into a ring. Wrapped around it are the magnets, which are nothing like the magnets on your refrigerator. They are among the most powerful ever made, some taller than a 4-story building. And here we meet one more piece of beautiful physics. To make a magnetic field strong enough to cage a plasma at 150 million degrees, the magnets must carry titanic electric currents, and any ordinary wire would melt instantly from its own resistance. So ITER's magnets are wound from special metals that become superconductors, materials that, when chilled close enough to absolute zero, lose all electrical resistance entirely and let current flow forever without the slightest loss. To reach that state, the magnets are bathed in liquid helium and cooled to nearly -269 degrees, just 4 degrees above the coldest temperature that can possibly exist, colder than the empty space between the stars. Which brings us to the single most astonishing fact about this entire machine, one almost too strange to believe. Inside ITER, separated by only a couple of meters, will sit one of the hottest places and one of the coldest places in the whole solar system. A plasma 10 times hotter than the core of the sun, floating inside a cage of magnets colder than deep space. The fire of a star, cradled in a fist of ice, and the two will never once touch. The spine of the machine is a gigantic central magnet, built in the United States in 6 colossal sections, each heavier than a fully loaded jumbo jet, stacked into a tower so strong it could, the engineers like to say, lift an aircraft carrier clean out of the water. the donut chamber arrives as enormous curved sections of steel from Europe and Korea. The giant thermos that keeps the cold sealed in came from India. The brutal job of catching the escaping heat falls to a component at the bottom called the diverter, armored with tungsten, the metal with the highest melting point of all. The finished machine will weigh around 23,000 tons, heavier than 3 Eiffel Towers stacked one upon another, and every one of its millions of parts built on 3 continents must fit together to within a fraction of a millimeter. It may well be the most complicated object human beings have ever attempted to build. And here is the crucial thing to understand about ITER. It is not designed to send a single watt of electricity to a single home. It is an experiment, the deciding experiment, and its whole goal lives in one number, physicists call Q, the ratio of the fusion energy you get out to the heating energy you put in. For 70 years, every fusion machine ever built had a Q less than 1. It always took more energy to run than the fusion gave back. We were forever spending $1 to make a dime. ITER is built to shatter that barrier. Its target is a Q of 10, to pour in 50 megawatts of heating power and get back 500 megawatts of fusion power. 10 to 1. It would be the first machine in history to produce vastly more energy than it consumes, the long-awaited proof that a star in a bottle can truly be a source of power. There is one more piece of cleverness ITER must test, and it solves fusion's last great puzzle, the fuel. ITER fuses deuterium and tritium, and while deuterium is everywhere in seawater, tritium is so rare and so quick to decay that there is almost none in all the world. The answer is one of the most elegant ideas in the whole enterprise. When deuterium and tritium fuse, they fling out a fast neutron, and that neutron, having no electric charge, sails right out of the magnetic cage and buries itself in the wall. So, future plants will line that wall with a blanket of the metal lithium, the very same lithium in the battery you may be holding right now. And when the fusion neutrons strike the lithium, they transform it into fresh tritium. The reactor breeds its own fuel as it burns, neutron by neutron, an endless loop, and proving this can actually be done is one of the great missions ITER carries. Now, we must be honest, because real science is honest. Fusion is hard, and it has always been harder than anyone hoped. People have joked for decades that practical fusion is 30 years away and always will be, and ITER itself has run years behind schedule and well over budget. The plasma's own temper is the first enemy, throwing off sudden storms, and keeping it calm minute after minute is like balancing a hurricane on the tip of a pencil. The heat is the second, pouring onto the diverter in loads fiercer than a spacecraft falling back to Earth. And the relentless rain of neutrons slowly damages the very steel of the machine, a third frontier all its own. But none of these problems break the laws of physics, not one. They are engineering problems, hard and stubborn and beautiful, and if history proves anything, it is that human beings, given time and cooperation, are extraordinarily good at solving those. And here is something wonderful that often gets lost. ITER is not racing alone. All across the planet, the dream is catching fire. In England, the grand old jet ran its final experiments in 2024 and went out in a blaze of glory, producing 69 megajoules of fusion energy in a single 5-second pulse from just 0.2 of a gram of fuel, the most ever recorded, a perfect dress rehearsal for ITER. In China, a tokamak nicknamed the Artificial Sun held a plasma steady for more than 1,000 seconds, nearly 18 minutes, in early 2025, and weeks later, a French machine pushed that endurance record past 22 minutes. In South Korea, a reactor reached 100 million degrees and held it for 48 seconds. In Germany, the beautifully strange, twisted stellarator called Wendelstein has been proving its sculpted magnets can hold plasma smoothly and steadily. And on the other road entirely, in December of 2022, scientists in California fired 192 lasers at a peppercorn of fuel and, for the first time in history, got back more energy than the lasers delivered. A tiny star alive for a few billionths of a second, made by human hands. They have repeated it many times since, with ever larger yields. The proof is in. The dream is not a fantasy. And that proof has lit a fire under a whole new generation. Alongside the great public projects, a booming crowd of private companies, many founded by young scientists and fueled by billions in investment, is now racing to build reactors of their own. some using a new kind of super powerful magnet to chase the same goal in a fraction of ITER's size, aiming to reach it within just a few years. There are many roads up this mountain now, and for the first time in 70 years, the whole world is climbing it at once.
Even ITER is not the final step.
Beyond it waits a machine already on the drawing board called DEMO, the demonstration plant that would at last take fusion's heat and send real electricity flowing into ordinary homes.
ITER is the proof.
DEMO is the promise, and the world it points toward lies just beyond. So let us go back one last time to where we began. To you, standing outside, with the warmth of the sun resting on your hand. For the whole of human history, that warmth was a gift we could only receive. We could feel the fire of the stars and measure it and wonder at it and worship it, but we could never make it. And now, in a field in France and in laboratories scattered across the earth, our species is doing something no creature on this planet has ever done. We are learning to build a star. Not to destroy with it as we first learned, but to power with it, to take the same fire that lit the first sunrise and forged the iron in our blood and kindle it gently, safely, on purpose, to light the bedrooms of our children. It will not be finished tomorrow.
The men and women building ITER know they may be laboring for a prize their grandchildren will collect.
Planting a tree in whose shade they will never sit, and doing it anyway because some dreams are worth 100 years of work. We are the part of the universe that woke up, looked at the stars, and asked how they burn. And then, astonishingly, we reached up and began to build one of our own. The fire of the stars is coming home.